You all to the Research Spark YouTube channel. So today we are going to discuss about the unit second, that is the magnetostatic and Maxwell's equation in this course electromagnetic theory and interference. Here is the syllabus for the second unit. So in this session we are actually going to talk about the energy density in the electrostatic field, Biot law, magnetic field intensity due to the infinite, finite and semi-infinite. Then we'll see the Ampere's law and their applications. So first, let's discuss about the energy density in electrostatic field. So actually, what is our target? Our target is to find out the energy density and total energy while we are bringing the some electronic energy in some field. So this is our target. So how we'll find out? So first, suppose if we are bringing the some charge Q1 from infinity points to the some field P1, then the energy will be the W1 or the work done. And then similarly, if we are bringing the charge Q2 in the some field, that is at the point P2, then suppose the charge, the W2 will be the energy, and similarly W3 will be the energy if we are bringing the another point third. Similarly, we can also find out the W4 and Wn if we are bringing the different charges in this particular field. And then since initially there was no charge, that is why no electric field, so W1 will be 0, and W2 now, since the Q1 has already placed in the field, so now your energy will be Q2 V21. V2 is only the potential, charge is Q2. So Q into V is the energy. Similarly, if we are bringing the Q3 in this field, then work done will be the Q3 V31 and plus V32. That is the total potential into the charge. Now, if we'll bring in the same in the reverse order, then we can find the energy again. That will be the 0 plus Q2 V2 3 plus Q1 V12 and V13. Now, if we'll add both the equations, that is, in if we are bringing in the charging and discharging, that is, if we are bringing in the charging points and then the reverse order, then we can find out the total energy that will be equal to the W is equal to half of Q1 V1 plus Q2 V2 and Q3 V3. So this is the valid for the 3 points, but similarly we can also find out the energy for n points, and in general this energy density will be W is equal to half of K is equal to 1 to N Q K and Vk. Now, this is the only for the point charges, but in general, if we wanted to find, like here, then WE will be that half of rho LV DL for line charges, for surface charges and volume charges. We can find out. Now, for if we have wanted to find out the general, then WE can also be written for the line charges. It will be for volume charges. It will be half of del divergence of dV dV, as rho V is equal to divergence of D. Now we'll use some the vector scalar the vector calculus, and then we can find out the value of WE, which will be after using this divergence of V of A, that is a scalar quantity. We will get the value WE is equal to the minus of half divergence of del of V into dV. Finally, we'll get the value WE is equal to half of D into E into dV. That will be equal to half of integration over the epsilon naught E square dV. Epsilon naught is the permittivity and the E is the electric field. So this is the general for the volume charge. Now let's talk about the Biot-Savart's law. So Biot-Savart's law will tell you the magnetic field intensity. Actually Coulomb's law is telling how to find out the electric field or the electrical field here force. Here exactly we will find out the similarly we'll find out the magnetic field intensity, that is del of H. So this is telling that at any point P, the differential current element, that is ID, is proportional to the product of IDL and the sine of angle alpha between the elements and the line joining P. So and the element is inversely proportional to the square of the distance R. So dH can be written as equal to the K, that is constant, ideal, that is the current, and sine alpha, that is the angle, and divided by R square, that is the distance from the elements I dl. So if there is a one thing, it must have the current carrying. If there is no current, means ideal will be equal to 0, and also R should be the at the some distance. So this is actually the way to find out the magnetic field intensity. Now, magnetic field intensity can be found for finite, infinite, or semi-infinite line charges. So here, suppose there is a finite line charges A and B, and if we wanted to find out the magnetic field due to this finite length A and B at point P, how can we find? So first, suppose on the line A and B there is a small element d of L. Let me denote, this is the d of L. This the line is A and B, and this is the d of L. So first we will target to find out the magnetic field intensity due to this small dl at this point P. So as per the Biot law, we know the dH is equal to idl. Idl will be the current which is carrying by this small element. Then cross R. R is the the distance from this element to the point P, and divided by 4 pi R cube. Now we'll find out the dl cross R. dl cross R will be the rho dz A phi, and then H, they will replace the value of dl cross R, and then we'll get this value. Here I rho dz divided by 4 pi rho square plus z square to the power 3 by 2. Rho square and z square is rho is this one, that is the point O to the H, the point P, and then the Z is O to dl. So since dl to point P is the R, so R will be the square root of this square, that is Z square plus rho square. Now, in order to integrate this one now only H, it is not easy to integrate. That is why let's replace the values of rho and Z, and the in terms of trigonometric. So how we'll do? So replace the value Z is equal to rho cot theta. Then differentiation, that is del Z equal to del Z will be the minus rho cos square alpha. Now replace all this value, you will get the value of H is equal to, and after integration you will get H is equal to I divided by 4 pi rho cos alpha 2 minus cos alpha 1. Alpha 2 is this one. Actually we are having the length of A to B. So A, the point P having the angle from point A to alpha 1 and point A to B to alpha 2. So we will integrate, we'll get. So this is actually the final value of the magnetic field due to the length the A and B carrying the current I. But now suppose this is the A and B length, means the finite. But if we'll find out due to the semi-infinite, then how much? So for the semi-infinite, just it will be actually the point P will be very close, and then we will replace the values. Then we'll get the value H is equal to I divided by 4 pi rho here. Cos alpha 2, that is equal to the 90. So that is why it will be cos alpha 2 will be 0 and alpha 1 will be equal to the 0 degree, means the 1. So finally we'll get due to the semi-infinite, means the magnetic field intensity due to semi-infinite will be equal to I divided by 4 pi rho. Similarly for infinite, alpha 1 equal to 180 and alpha 2 will be equal to 0, and if we'll put the values here in the finite one, you will get the value of H is equal to I divided by twice pi rho. Now let's talk about the Ampere circuit law. So Ampere circuit law states that the line integral of the tangential component of H around the closed path is same as the net current I enclosed by path. Means in short, H dot dl is equal to I enclosed. So H is your field intensity. So field intensity across this L integration is equal to the total current carrying in that loop. So that is the Ampere's law. So this is very similar to the Gaussian law. So this is the main formula that you should remember. That is SDL is equal to I enclosed. So this is a very important Ampere's law, will be used to find out the magnetic field intensity. Now how will we find out the I enclosed? So it will be equal to I H dot dl and we can change linear integral to the surface integral. So h del cross h is equal to ds. So finally your I enclosed will be the j dot ds. J is the current density, ds is the surface. Also we can replace it, that is del cross h is equal to j. So h is the magnetic field intensity, j is the current density. So we'll use this one primarily equation, that is integration of hdl is equal to I. As for example, let me find out the magnetic field intensity due to the infinite current. So suppose this is the wire, and the infinite wire, that is the this one, and the ampere path. Major challenge is to find out the ampere path. So here ampere path will be the circular. So this is the ampere path. Now I is equal to, actually formula is that, if you remember, that is the HDL is equal to I enclosed. So first target is to find out the I enclosed. So I enclosed will be H dot DL. So here H phi and DL will be actually the, suppose the element, this one element, that is the, suppose the radius is rho, then the small element will be the rho into d phi. And so rho into d phi will integrate, means the entire circumference of the circle. So circumference of the circle is twice by rho. So then finally I is equal to h twice by rho. So h will be I by 2 by rho. Similarly, for infinite sheet of current, suppose this is the infinite sheet and the current is passing through in this horizontal manner and ampere path is vertical. Okay, so there is now there is a component, that is dh, and so dh x and y in this direction, that is in r. Now here, so our objective is to find out the total dl, that is h dot dl is equal to I enclosed. So how we'll use here? So since suppose HDL is equal to ideal, since current is passing, that is K of YB. So this will, the field will have the two direction, that is H of A of X and H minus of H of A into X. Either in this direction or in this direction. In other two direction, your field will be 0. So 1 to 2. Suppose the 1 to 2 and 3 to 4 both will be 0, and the vertical, that is 2 to 3 and 3 to 4 will not be 0, because current is passing in this direction, and in the vertical direction no current, means since current is passing only in the y direction. So that is why ampere path having the the magnitude only in the loop number 2 to 3 and 4 to 1. Just put the values. So 0 into minus 0, why? Because this is vertically no current, current is passing in this horizontally, so that is why 0. And then 2 to 3, 2 to 3 this loop, so current is passing this region, so that will be h into minus v length. Length is minus v, and then third one, that is the this one again. So no current is passing in this region, so 0. And then this one, in this direction we are coming, so now it will be plus. So h dot b length is same. So twice of HB total, now H dot dl. Now finally, so H is equal to half of KYX and then minus of. Finally, we can write in general, that is H is equal to half of K into A. Now let's talk about the field intensity, that is magnetic field intensity due to the infinite long coaxial transmission cable. So here there are the two different the circles. So first inner circle, this one having the radius a, and there is another circle, this one having this cable have the radius of b, and the thickness of outer cable is suppose the t. A variable is rho. Rho is variable, means actually our target is to find out the field intensity at 4 points. First, inside the inner cable, means in this region. Then we'll find out the outside to the inner cable, means and before the outer cable, means in this region, in this white region. Third point, we will find out the inside this outer cable, and finally we'll find out the magnetic field intensity outside to the inner outer both cable, outer cable in this region. So first here, second here, third in this outer, fourth here. So let's find out the four first. So actually our target will use the same Ampere's law, that is H dot dl is equal to I enclosed is equal to J dot ds. So our objective is to find out the I enclosed because current will be lesser for this entire region. So suppose current is passing I and minus I through the I in the inner cable and minus I through the outer cable. So first inside this inner cable we will find out the current in this region. So current density will be I divided by pi a square. Pi a is the inner radius and then ds will be rho d phi d rho surface area. Then I enclosed we can find out that will be equal to I rho square by a square. Using this I now we can find out the h which will be equal to I rho by twice by a square using the same Ampere's law. Now let's find out the variable rho is in between the A and B, that is the in this second region. So here since now the entire the inner one is enclosed, so current will be now no need to find current will be the total I and the ampere path having the radius rho. So h of twice by rho equal to I, so h will be I by twice by rho. So we have already got the two values. Now let's find out the third. So for third one, that is the row variable is in between b to b plus t. So here again, now h dot dl will be, suppose the outer thickness is very less. In that case, h into twice pi phi is equal to I enclosed, and so I plus j dot ds. So this is challenge is to find out the j dot ds because I current carrying through the inner cable. Now whatever the portion we are covering the outer cable, due to that we have to find the current. So how we'll find out? So current will be find out using this technique here. So again the density, that is I divided by pi b plus t whole square minus b square, this is the current density, and multiply that particular region, that is phi is equal to 0 to twice pi and rho is equal to b to rho. You will get the value of h is equal to I twice pi rho 1 minus b square rho square v square divided by 2 t square plus 2bt. Now at the last point means the rho is greater, the outside to the outer cable. In that case, since the total current is, the inside the inner cable is plus I and outside outer cable having the minus I, so total current will be 0. So finally H will be also 0. So here is the summary for inner circle. Inner cable will have the magnetic field I rho divided by twice pi square. In between the inner and outer, the magnetic field will be the I divided by twice pi rho. In between, in the outer region, I divided by twice pi to 1 minus rho square b square divided by t square plus 2bt. And outside to the outer region, magnetic field intensity will be 0. So this is the summary of the magnetic field intensity due to the coaxial cable. So in the next session, we will talk about these things, that is magnetic field density and some problems and Faraday's law and Maxwell equation for static and time varies. Thank you for listening in. If you have any problems, please drop your comments. Thank you.